Hello, and welcome to another DANTE tutorial video, this time on Heat Treatment Process Simulator, or HTP Sim for short. HTP Sim is a standalone finite element-based tool for modeling the entire heat treatment process from start to finish. Starting fresh with the materials section, HTP Sim uses the same validated material models of a full DANTE FEA package, combining the phase transformation models and the carbon and nitrogen diffusion models and the carbide nitride morphology into one complete process model. For this example, we'll be using 4120 material with 0.2% carbon. So we go down to the 4100 series material and ensure we have 0.2 carbon. We assume that it's free of carbides and nitrides and precipitates. And we assume that the material is fully annealed. For this material, that would be 70% ferrite and about 30% perlite. We assume the grain size and the alloy composition are nominal, but we can always change these if you have a different chemistry within the series. For the geometry tab, you can see that this is simplified into an inner and outer radius. What this means is basically the part section is simplified to the equivalent size, and the FEA model is built in the background. This is one of the simplifications that makes this very easy to use. For what that really means is if we have a cylinder shape or a ring shape, the little red line here is basically the one-dimensional finite volume that we'll be displaying in the results. So for the work that we're going to be doing here today, the 2-inch cylinder, like a solid shaft like the one we see at the bottom here, will be used to model the processes. But if you wanted to use the ring shape, this is really good for gears, bearing rings, and hollow shafts where you have an inner diameter that has heat transfer. So to set that up in the HTP Sim utility, we would say that there was 0 inner radius to make it a cylinder, and then the outer radius is 1 inch or 25.4 millimeters. Now we come to the process tab, and today the process being modeled is on the next slide. And it includes, you can see the results of the output here, but it includes a furnace heating to 900 degrees C and then soak for 20 minutes. Then there's a gas carburization at 0.9 carbon potential for about 8 hours at that 900 degrees C. And then before quenching, they're going to ramp down to 860 degrees C, oil quench in 50 degree C oil. There will be a direct tempering to 220 degrees C, and then final room to air-cooled temperature. And for this process, we're going to be using the equipment module, which can be used when selecting and setting up the boundary conditions of the process. And this really simplifies the process and makes it go much easier for your heat transfer coefficients. So starting with this process tab, we have the initial temperature of 20 degrees C, and we'll insert a step so we can do furnace heating. We will name this furnace heating. And we'll keep it at about 2 hours for the process, given the section size is about 2 inches. For the equipment module, the next thing we have to do is define the temperatures and the heat transfer coefficients. But for the equipment model, we can quickly select the heating furnace here, and this automatically sets the heat transfer coefficients based on the surface temperature for the part. For the process here, we will be at 900 degrees C though, and so we would set this as basically a tabular function, so to keep it at 900 degrees C ambient temperature for the whole process. After that, we got to go into our carburization process. So we would select the type of gas carburization, and the time here would be 8 hours, so this is 28,800 seconds. Gas carburization is what we will name the description here. And then again, for the equipment module, to make things simpler, we will select the gas carburization furnace, and now we just need to define the carbon potential in this furnace, which is 0.9. And then that is the carburization step. After that, we will be doing a ramp down to 860 degrees C. This takes only 1 hour. Ramp before quench. And again, we will use the heating furnace that we have already set, and we will use the temperature to ramp down to 860 degrees C. Again, the heat transfer coefficients are automatically defined with the equipment module. We will insert a step after that ramp, and we will now oil quench. Let's take about an hour for the oil quench. And we will use the custom oil quench tank material that we have built into DANTE. The temperature of the oil tank is a little bit lower, it's 50 degrees C, and the heat transfer coefficients again are automatically populated by the equipment. So after quenching, we have an immediate temper, so we will do 2 hours of temper in the tempering furnace at 220 degrees C. And then lastly, we need to cool back to room temperature. So that's a thermal process, take about 2 hours, and we use the air cool temperature down to 220 degrees C. Okay, so with the process fully defined, we'll now look at the controls menu. The controls menu has a lot of different options for activating the different models inside of DANTE. For this model, we do have tempering, so we will activate these to include that in there. We have options for carbon and nitrogen effect on volume change. We have options for carbide decomposition, latent heat. We will apply that for heating and cooling for this module. We have the alloy carbide precipitation model. We don't expect any precipitates here with this material, so we will leave that off. We have the austenite grain growth model, and then a carbon partitioning model. The output frequency determines how many steps are actually shown in the background. So for this case, it'll be every 10th step will actually be shown in the results. For this, I'll bring this down to 5 just to show the cooling and heating curves a little better. For hardness units, we have HRC or Vickers, depending on which ones you would use. Temperature is degrees C or in Fahrenheit. The time is in seconds or minutes, and then the length could be inches or millimeters. The last thing is defining where the material directory is for DANTE. We're just going to leave this as default because this is good for what we're doing. And now we've set up a process here in just a few minutes, and we can run it. So the first thing we do is just go ahead and save it to a directory. I'd like to go to the temp directory here. We'll call this 4120 quench and temper QT. And then that's done. And that less than a minute, you have results. So post-processing. After analysis, when you hit the plot button, it plots the time versus temperature for the surface point by default. And you can see in the plot window here, we have a lot of different options that we can choose. And one good thing to start with is to look at the core temperature to make sure that you've achieved the core temperature during your process and when you actually did. So we'll go ahead and select the core node here, and then we hit plot. And we can see at the end of the heat up process, we are at 900 degrees C. So we have that 20-minute soak after that. And then we have 900 degrees C throughout the carburization process until the ramp down. The ramp down in temperature, the core does reach 860 degrees. It does quench down to 50 degrees C. And then 220 degrees was our tempering temperature, and 20 degrees C is our ambient cool to room temperature. So the core of the part did achieve the temperatures that we were looking for. So we can now look at the surface point, and we can look at the temperature, and we can start looking at the phase volume fraction. And we can see all phases through this process. So we can see we start off with the green and the red lines here with ferrite and perlite. And then as the heating continues in the furnace, this begins to decompose into austenite phase. And you can see we reach 100% austenite really quickly within the process. And so you could save a little bit of time with that 20-minute soak or so if you were going to be editing this process. We can see that we stay austenite pretty much the entire time through the carburization process until we get to the quench step here. And you can see as we quench, the austenite decomposes into the martensite phase. After quenching, we have about 81% predicted for the martensite, and there's a little bit of auto-tempered martensite, about 2% or so. Then we can look at the tempering step here, and we can see that the martensite decomposes into tempered martensite phase, about 83% or so of that, and there still is about 15 or so percent of retained austenite in the tempering phase. When we cool down from tempering, it goes through the MS temperature again, and this austenite begins to decompose down to about 6% into as quenched martensite, another 6% there, and then there's a little bit of tempered martensite that's left over from the cool down as well. It gets to about 86% tempered martensite phase during the process. Other things we can look at is the carbon and nitrogen profile. So we can look at this and look at the total carbon since we do carburize. We can plot this over the time, and we can see that once we start carburization, this is at the 0.2% for base carbon of this material, 4120. Then we can see the carbon ramps up on the surface relatively quickly and finally ends up close to the 0.9% carbon atmosphere that's in the furnace with 0.889 or so carbon. This stays constant at the surface through the rest of the process. Another way we can look at the data is to look at the profile of this cylinder, and by choosing the single increment. And then so the increment we're going to look at here is the final increment here, but we can look at any of these sub-steps during the process to see different changes throughout the process. So temperature isn't as valuable here. We can look at hardness. We can see the hardness profile, and then we'll leave total carbons. We can see both of those. We can close this window and zoom in to take a better look at this. We can look at the first 5 millimeters or so, and we can see that the hardness value is this black line here. We can see at the surface we should be about 60 HRC, and then the carbon is still the 0.89 we showed earlier. And then at the 50 HRC case depth, we're about 1 millimeter of depth. The carbon value, interestingly, at that time is about 0.36 carbon to achieve that 50 HRC after tempering. We can see if we go back to the original view here, we can see the hardness in the core was about 35 HRC, and with that 0.2 carbon, that this is base material. We could also look at the phase and volume fractions along with the hardness, and this is interesting because you can see through the case we have a lot of tempered martensite. It's about 10 millimeters here. And we can see we have mainly tempered martensite here with a little bit of as-quenched martensite and austenite, retained austenite, to a depth here of about 0.65 millimeters, a little over half a millimeter. We have the retained austenite and as-quenched martensite, and that's also where the peak kind of is for the tempered martensite, where the kind of coincides a little bit with the case depth as well. We can see in the core we are mainly lower bainite, about 50%, upper and tempered martensite round out the phases in the core of the cylinder. Those are the two different ways you can really plot and view the information. You could also view the information from the ID if you're looking at the ID and this was a ring model instead of a cylinder. You could also have the X coordinates so you can see the depth. 0 is 0 on your core, and then 25.4 millimeters is our radius. Other things that can be plotted are the iron carbides or alloy precipitates. We have those. They're not in this model, but if you do run those models, we can see those. We can see the carbide size if there is a carbide grain growth or carbide model, and then the austenite grain size for the grain growth model. And any of these process steps. So at the end of tempering here, the end of quench, we can plot the results and see the changes throughout the entire process. So that's what's really powerful about this utility. The big thing is that the utility is very easy to use. So anybody can follow this tutorial and in 15 minutes get valuable results for their process. We do have a large list of materials through, I think there was like 75 different standard materials in our database, as well as much more for different chemistries. And it's expandable, so you can apply your own materials to these processes. The geometry is simplified down so that you don't have to worry about meshing and complicated algorithms. And then the process, with setting up the processes, you can apply your own equipment in order to get these heat transfer coefficients to make it easy to apply. So you know the behavior of your heating furnace, or you know your behavior of your air cool, and you can use those HTCs predefined and then just apply them. And finally, viewing the results is very simple. Plotting it, you can see at different points you can get information very easily with the plotting function. And we hope that you find value in these tutorials that we create here. If you have any questions, go ahead and email us at support@dantesolutions.com, or you can view other animations and videos like these on our website at dante-solutions.com. Thank you.